I now call to order the Society's 2,492nd meeting in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and to lectures by Tom Karr and Jim Trebes. Let's start by thanking our sponsors. First, the Society is grateful to PSW Full Year Series sponsor, PSW member Mike Helton and Helton Associates, LLC, for their support. Thank you, Mike. And to Edward Gaddisoo, another PSW member, for sponsoring tonight's lecture. Thank you, Ed. I'm pleased to note that the following new members have been admitted to the Society. David Graham, U.S. Navy Chief Petty Officer, retired, and Computer Systems Administrator, interested in astronomy, cosmology, geology, and anthropology, who found out about PSW by running across videos on the PSW YouTube channel. Abigail Moore, a new student member and cybersecurity expert with the DoD, interested in a broad range of subjects, particularly recent scientific research, including nanotechnology, genetics, and space, who learned of the Society through current PSW members and by attending a PSW event. Thomas Swidajewski, a new student member and a program manager with Ignite, interested in emerging technologies and cognitive science, who learned of PSW from a member of the Cosmos Club. Victoria Sheets, an attorney with the U.S. Attorney's Office, interested in emerging technologies and biotechnology, including issues they pose for society, who learned of PSW by looking for interesting lectures after moving here from the Big Apple. And Jessica Rosarda, professor of cell biology at the Uniformed Services University, interested in cell biology and genetics, machine learning and AI, science, ethics, and healthcare, who learned of PSW from Meetup. Jessica is a former member, rejoining now that she's returned from her graduate studies in San Diego and at my alma mater of sorts, Scripps Research. And tonight's speakers, Tom Karr and Jim Trebes, who learned of PSW science from our invitation to them to speak here tonight, and whose interests will be clear in part from tonight's proceedings. If you're interested in membership, you can access a membership application form on the PSW website homepage, where there is a blue join button in the upper right-hand corner. And if you press that blue join button, you'll call up the membership application form, which you can fill out and pay your $75 and almost certainly be admitted to membership. All members are entitled to a signed copy of Volume 1 of the Bulletin of the PSW, and if they so choose, to wear the ribbon of the Society. If you're a new member and you haven't received your signed copy of the Bulletin, please come see me after the meeting, and I will be happy to provide one to you. Recording Secretary Scott Matthews will now present the minutes of the 2,491st meeting and the lecture by Eric Klein on the survival of civilizations after the Bronze Age collapse of 1177 BCE. Scott, stage is yours.
Thank you, Larry. Good evening. On March 8th, 2024, in the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2,491st meeting of the Society to order at 8:08 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Bartok Rajwa titled Spectroscopy of Deception, Unmasking Food Fraud with Biophysics. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Eric Klein of George Washington University. His lecture was titled Survival of Civilizations After 1177 BCE. The speaker began by noting his previous PSW lecture in 2015 on the events leading up to 1177 BCE, and stating that the present lecture would be a sequel detailing the response of several civilizations to these events. Klein showed a map of the, quote, G8 of the Late Bronze Age, which included the civilizations of the Mycenaeans, Minoans, Egyptians, Hittites, Canaanites, Cypriotes, Assyrians, and Babylonians. He showed a diagram of the trade routes connecting these 8 major civilizations as well as 4 smaller civilizations, which constituted a, quote, small world network, in that each society was not more than 3 hops away from all the others. Klein said that within a few decades of 1177 BCE, all of these trade routes and many of the trading civilizations had collapsed. The speaker said that while the collapse at the end of the Late Bronze Age was not well known, the magnitude of the catastrophe was enormous, comparable to the fall of the Roman Empire. Klein stated that he believed that this collapse was caused by a number of factors, occurring simultaneously or in rapid succession, including drought, famine, earthquakes, and invaders. He then showed archaeological evidence for each of these factors occurring during this period of time. Klein then stated that the Late Bronze Age collapse constituted a, quote, systems collapse. He defined the specific features of systems collapse. 1, the collapse of central administrative organizations. 2, the disappearance of the traditional elite class. 3, the collapse of the centralized economy. And 4, settlement shifts and population decline. He indicated that in response to this systems collapse, some civilizations did better than others. Klein then presented the concepts of resilience, anti-fragility, and the adaptive cycle, discussing how these features increase the capacity to recover from extreme impact events. He noted that while many of these ideas were taken from modern IPCC documents written in consideration of climate change, all the concepts and definitions were accurate and appropriate for the recovery from the Late Bronze Age collapse. He then compared the response of each individual society to the collapse using the previously defined concepts of resilience and adaptation as metrics. He gave each society or geographic area a numeric score. He indicated that while he may have, quote, massaged the numbers using his gut feeling, he was quite confident about his final ranking of the civilizations. The end result was Phoenicians and Cypriots were anti-fragile, having the highest score. Assyrians, Babylonians, and Neo-Hittites were resilient. Egyptians were adapting. Mycenaeans and Minoans were not resilient, but had some survivors. Hittites and southern Canaanites disappeared and had the lowest score. Klein then went through specific arguments justifying the rankings of each of these civilizations with evidence from the archaeological record. He provided evidence that some members of the poorer performing societies, like the Hittites and the southern Canaanites, may have been assimilated into more successful societies. Klein ended his lecture by arguing that the analysis and the discussion of the response to the Late Bronze Age collapse is directly relevant to, quote, what is happening to us today with climate change, a pandemic, social upheaval, supply chain issues, and so on, end quote. The lecture was followed by a question and answer session. One member asked a question concerning the Dorians. Klein responded that there is no historical evidence for the Dorian invasion. A non-member asked a question about the quote-unquote explosion of ancient DNA and the impact on Klein's research. Klein responded that several recent results of aDNA, or ancient DNA, have significantly impacted his research, and that he believes that aDNA may constitute a significant part of a, quote, third wave of modern archaeology. A member asked about the details of what happens to the people living in a city when the city falls or is conquered by invaders. Are the people slaughtered or do they flee? Klein responded that both death and migration occur to varying degrees. He gave examples where a significant fraction of the conquered population flees and migrates into another group, and others where large fractions of the population die either at the hands of the invaders or in the aftermath. A viewer on the YouTube channel asked how the collapse impacted the sea trade around the Mediterranean. Klein responded that for a period after the collapse, possibly several decades, the trade network was, quote, broken, with imports being drastically reduced in all areas affected. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers for upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,491st meeting of the Society at 8:18 p.m. Eastern Time. Temperature in Washington, D.C., 10.5 degrees Celsius. Weather, mostly cloudy. Audience in the Powell Auditorium, 93. Viewers on the live stream, 52, for a total of 145 live viewers. Views of the video in the first 2 weeks, 1,716. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. I have one correction to the way you read the minutes. You said it was adjourned at 8. You said it was adjourned at 8:15? I think you meant 10:15 or something like that. Yeah, maybe my hearing's wrong. I think you said 8, but anyway, is there any other important suggestions or corrections to the minutes? Hearing none, I will entertain a motion to accept the minutes as read. Is there a second by a member? Do we have all in favor? All members in favor of accepting? All members opposed? Hearing no opposition, the minutes are accepted as read and will be posted to the website. If there's anybody online who has any suggestions or comments, please send them to corresponding sec at pswscience.org. And we now turn to tonight's lecture by Thomas Karr and James Trebes. Tom is Chief Scientist for Sensors and Directed Energy at MITRE Corporation. He is also consultant to the Defense Science Board and the Air Force Scientific Advisory Board. And he is the owner of Alamo Scientific LLC. Tom's research interests include national economic and military security strategy, remote sensing, space industry development, quantum sensing and information, and electromagnetic propagation and interaction with materials. Among many notable accomplishments, Tom led the development of autonomous GPS-independent precision navigation systems, high-resolution synthetic aperture laser radar, and the first system for predicting Scud missile impact points while in flight. He also discovered fundamental properties of high-power laser propagation and a new relativistic wave equation for interacting spin 1/2 particles. He is an author on 64 publications in scientific journals and an inventor on 3 patents, and he is the recipient of many honors and awards, among which I will only mention that he received the DARPA Meritorious Public Service Medal. He is an optical fellow, a fellow of the Military Sensing Symposium, and a fellow of the Society of Photo-Optical Instrumentation Engineers. He earned an AB in physics at Princeton and a PhD in physics at the University of Maryland. Jim is a consultant for the Office of the Undersecretary of Defense for Research and Engineering, for the Missile Defense Agency, and for the Defense Science Board. Previously, he was principal physicist for directed energy at OUSD and the principal director for directed energy. And before joining OUSD, he was with Lawrence Livermore Laboratory for almost 40 years, where he served as a leader of several divisions. He has worked on X-ray lasers, laser fusion, nuclear weapons physics, nuclear weapons engineering, X-ray optics, X-ray imaging, space technology, detectors, biophysics, biodetection, night vision, tomography, nuclear nonproliferation, quantum science, and other fields. He's an author on 62 scientific publications and an inventor on 7 patents. Among other honors and awards, he is a fellow of the American Physical Society and has served on advisory boards for both Texas A&M Aerospace Department and the UC Berkeley Nuclear Engineering Department. Jim earned a BS in physics at Georgia Tech and a PhD in physics at Yale. The lecture will be done jointly by Tom and Jim, and after the lecture, the two of them will sit down and have a colloquy, also known as a debate, about their differing views on directed energy weapons. And we will then have a Q&A session, and all questions will be held for that Q&A session. All right. With that, turn the stage over to these two speakers.
Thank you, Larry, for that generous introduction for both of us. It is a privilege to speak to you, to be invited to give this talk to you. If you seek peace, then prepare for war. This talk is a little different than some others I've seen on YouTube, which are often for pure science and academic and scholarly research. Here we're talking about applying some cutting-edge physics and technology towards making a new kind of weapon. I'm going to talk to you about the status of that, what works, what doesn't work, and what the challenges are in the future. We're going to alternate through this as we go down these bullets. Jim's going to speak on what a directed energy weapon is, what makes directed energy into a weapon. I'm going to talk about some history, what has worked and has not worked in the past, and why things seem to be much more optimistic, much more favorable today. Jim is going to talk about what makes a directed energy weapon lethal, how does it affect materials, how does it affect other weapons, incoming threats. I'll talk to you about the current directed energy weapons that are actually in the field and that are going to be in the field, we hope, soon, including also the foreign systems. Many other countries are developing this technology. Jim will talk about the military challenges, the military issues, the problems with directed energy. It's not all good news. There's some bad news that has to be overcome. And then after we talk a little bit about what the future might be, we'll have a collegial debate. Okay, the balance of this talk is it's almost all about laser weapons. We'll talk a little bit about microwave weapons, although there's less that we can say about those, and we have essentially nothing to say about particle beam weapons, which have been researched in the past. We're going to talk about the physics of how they work, the lethality, and the limitations. We're not going to say anything about less than lethal systems. So, be happy to talk to you about some of these other topics when we get done with the body of the talk. I just want to point out, here's Star Trek, my favorite TV program from when I was a teenager in high school. And back in the 1980s, when directed energy was being touted by its proponents to do strategic defense against ballistic missiles, I actually had one of these posters on the wall in my office. I wish I still had it. It got lost somehow among them, moving between houses for 40 years. It would be a great collector's item to donate to the Smithsonian at this point. But people actually had stuff like that on their walls. Defense at the speed of light. We were going to put these battle stars in space. So we'll talk about some of this when we get to the history section.
Thank everybody to be here to help give this talk. You know, the question is, where does directed energy fit in the technology world? The White House Office of Science and Technology Policy has created their list of critical technologies that are both required for continuing developing prosperity for the nation and for the national security. And right there in the middle is directed energy. And then the Defense Department has its list, smaller list, 11 topics, for which they've created principal directors to oversee the development and deployment of those technological capabilities. And Tom was the first principal director for directed energy, and I was the second principal director for directed energy. And we started working together, we continue to work together, and we continue to argue. But directed energy is a key part of the, sometimes he's even right. Directed energy is a key part of the developing technology of the country. So what are directed energy weapons? It's basically you're going to create a beam of energy and send it onto a target where it's going to interact with that target and create some military effect. It could be you're disrupting it, you could be damaging it, it could be destroying it. There's a wide range of effects. We'll get into that and later. You know, so why bother? We have lots of weapons, all kinds of weapons. So what's new here? What does it really offer? One of the key points is there's the potential, I'll say potential, for what's called a deep magazine. Missile launchers run out of missiles. Machine guns run out of bullets. Directed energy weapons, as long as they have power and cooling, keep shooting. And so in principle, they can shoot forever. In practice, that is not true. There's usually limited cooling and limited power available, so there is a magazine size. But potentially, these are very cheap, few dollar shots from a very expensive system. Instead of using a very expensive missile. And so there's a lot of potential to what we call bend the cost curve. Missile launchers are relatively cheap. Missiles are very expensive. Lasers, microwave weapons are very expensive, but their bullets they shoot are very cheap. So it's a different way. You get precision effects. You can point these things. You can aim them. And so collateral damage is considerably reduced. You know, I can hit something at 20 kilometers, a spot that big, and I can maintain it, and I can hit it again, and I can hit it again. The precision is remarkably impressive. You engage at the speed of light. I don't have to worry about bullet drop. I don't have to worry about wind. I don't have to worry about Coriolis effect. I can point it. It's going to get there. It's going to get there now. You know, bullets can take seconds to minutes. Missiles can take seconds to hours to get to their target, not with the speed of light. And you can use them anywhere, air, land, sea, space, anywhere you can squeeze one in. And so there's various pictures of various systems. We'll go through pieces of those as the talk goes on. You'll get to see more about them, so I won't do it now. And, you know, the bottom line question is what's not to like? Well, by the end of the talk, you'll probably find out there's a lot not to like, but we'll go through all of that. So how does it become a weapon? Well, you have to have a source that makes your energy. You have to turn it into a beam with a laser. That's some kind of optical telescope. With a microwave system, that's some kind of curved antenna. Both the microwave weapons, high power microwaves, HPMs as we call them today, and the lasers are both electric. The microwave systems can trace back to vacuum tube technology from pre-World War II radar. It's evolved a lot. The materials are better, the performance is better, but it really does trace to that. The new lasers are based on the telecommunications industry use of fiber optics and light emitting diodes and laser diodes. And so most of the lasers highly leverage the telecommunications industry, which helps reduce their costs significantly. There's different kinds of laser systems. There's continuous, the blowtorch approach, where you're going to melt a hole in something. There's pulsed, where you're going to, you could fracture, you could create spall where fragments from the inner side of the wall propagate into the object, destroying it. You can create shocks, you can create disruptions in airflow. You can create RF effects with lasers impacting on them. There's a wide range. There's a whole zoology of potential effects, and we'll get into some of that. Microwaves, you're essentially using the high electric field to drive electric currents if you can get into the electric circuits inside an adversary weapon system, you can cause reversible effects, i.e. you could flip a bit in a computer system and screw up their software processing and force them to do a reset. Or you can fry that bit. Or you can fry an amplifier, causing permanent damage and everything in between. So there's a growing interest in that in directed energy, and it's this cost question. There's a lot of missiles out there now. There's a lot of countries fielding a lot of missiles. They're fielding large numbers of artillery shells, mortar shells, drones, subsonic cruise missiles, supersonic cruise missiles, hypersonic missiles, ballistic missiles of all ranges. And it's not 10 or 20, it's thousands and tens of thousands. It's a large number. And if you're trying to defend against those, you ask, if I'm going to use a conventional missile system where I'm using a defensive missile, I need a lot of those, and those are very expensive. And so you go, I can't afford this. I need a better way. And, one way that you can see on the bottom right, these are the Iranian drones the Houthis are using to cause all sorts of grief in the Red Sea. They come 5 to a truck. You can launch them all. They're about $10,000, $20,000 a piece, and they wreak havoc. These are the Chinese hypersonic missiles they're now deploying in large quantities. Again, they can wreak a lot of havoc. And one way to think about it in terms of trade-offs, I've got a guided missile destroyer. The typical one has about 96 missile tubes, which means it has about 96 missiles. Some of them are defensive, some of them are offensive. There's various missions are filled by different missiles, but you could guesstimate about half are defensive. Sometimes that might even be true. The exact ratios and are mission dependent, and the Navy's not going to tell us. If I have 48 incoming missiles and I've got 48 defensive missiles, I think I'm done, and I got to go home. I can't stay in theater. Reloading a missile tube at sea in combat is, for the very daring maneuver, hard to do. And so I need deeper magazine. And so the value of directed energy starts to climb remarkably as a war progresses. As I shoot more and more missiles because I have to, and my tubes are running empty, what am I going to do? So this is the challenge we're facing, and the question is directed energy going to solve this problem? There is a roadmap for the development of directed energy weapons for the Department of Defense. This was actually, the first version of this was actually created by Tom. It's a spiral development plan. The goal here is advance the technology, improve your ability to do things in a steady way, measured way with research and development. Builds operational systems, one of a kinds, few of a kinds, get them in the field, get real military people operating them. It's one thing for Tom and I and a bunch of PhD scientists to operate a laser. It's another thing for some corporals and sergeants to operate a laser. How does that really happen? How do they do that? Well, you have to learn how the real world works and what breaks and what doesn't, and then start to deliver new military capabilities and eventually achieve military dominance everywhere directed energy makes sense. Not everywhere, but everywhere it makes sense. It's not a silver bullet for solving all problems. And it's basically a stair-step approach. And so right now what's happening is tactical missions are getting addressed by today's technology. It's shooting down mortar shells. It's shooting down small rockets. It's shooting down small drones. It's using 10 kilowatt, 20 kilowatt laser systems on small vehicles. You want, as the technology advances, and it is advancing, and we'll go through a lot of that, you want to begin to address the cruise missile problem. There are a lot of cruise missiles out there. That's a bigger, for laser point of view, 200, 300 kilowatt lasers are needed to really address that. And then long-term down the road, you want to get back to the strategic mission from SDIO days, the original Star Wars program. What can we do about ballistic missiles and hypersonic missiles? I can tell you, we'll talk about it during our debate. It's a very hard problem, and we are definitely not there yet. I can tell you that, I inherited Tom's roadmap, and what change did I make? And the current principal director for directed energy, Frank Peterkin in the Pentagon, likes to joke that I added the 2 arrows. And so we started to accelerate what we're doing about counter hypersonics and counter cruise missiles. And I will turn it over to my colleague.
Thank you. Thank you. Okay, now now we get to a little physics. And again, we're talking mostly about high energy lasers, high power lasers. The lasers have to operate in the so-called atmospheric windows. They have to work at wavelengths that will get through the air. So here I'm illustrating windows from the long wave infrared through short wave infrared. This is in the so-called shortwave infrared, and then finally we get into the visible. And they're all different kinds of laser technologies that fit into these windows. And the laser enthusiasts have worked on all of these windows. They started out with the long wave stuff in CO2 lasers, and then went to these deuterium fluoride, hydrogen fluoride, which are mid-wave infrared chemical lasers. Then the next one that was very popular is this chemical oxygen iodine laser at 1.315 microns. Fortunately, it's in a place where it just managed to get through the atmosphere. And now we are in the era of solid state, mostly solid state lasers, solid state fibers, ytterbium glass fibers that operate around 1 micron, and using diode pumped alkali lasers also that operate just below 0.8 microns. Okay, so you've seen this progression over the course of 60 years from long wave infrared, short wave, finally down to the visible. And I say it's 60 years. It is 60 years. We'll get to now some history. Actually, you can go back over 2,000 years. The Syracusan Defense Advanced Research Projects Agency, led by Archimedes, proposed the first directed energy weapon. And consistent with the history of directed energy weapons, it turns out this doesn't work. It was proven by the Mythbusters TV show. They tried to reproduce this. It doesn't work. The first laser demonstrated in 1960, Ted Myman. Now, DARPA was founded in 1958. In 1960, the first laser was demonstrated in a laboratory. By 1961, somebody submitted a proposal to DARPA to build a laser which would have 1 cubic meter of ruby rods. And Myman had this little ruby rod with flash lamps. Somebody proposed to build a giant laser with 1 cubic meter worth of ruby rods that would produce 1 megajoule pulses that would destroy incoming ballistic missile warheads in the sky. It only took a year for some guy. Now, that laser never got built, obviously. But as soon as people came up with the laser, people were proposing to use it for destroying targets, especially for strategic defense. I want to point out that when these chemical lasers became popular, which was in the 1970s, the deuterium fluoride lasers go through the air. Now, it's a little hard to see the picture. It's small, but this building is filled by this megawatt class laser called the Miracle mid-infrared chemical laser. It's a little hard to see there, but there's a control panel, and there's a platform that a person can stand on. There's a bunch of little dials, little valves that somebody can handle. And this huge building, this laser filled this huge building. And that's the beam director that would transmit this laser to shoot down cruise missiles. And there is a person, a man, standing next to it. Can you see how small that guy is? Somehow, people convinced Navy admirals that this was someday going to be on a ship and defend a ship against cruise missiles. Okay? But that's the scale at which things were done. There was huge facilities. In 1987, well, in 1984 to I think it's 82, Reagan gives his Star Wars speech. We're going to defend against ballistic missiles somehow. The laser world went crazy with that. They said, this is our day. Finally, we're going to build laser weapons to defend against ballistic missiles. In 1987, the American Physical Society published a report. They had convened a panel of eminent physicists led by Nicholas Bloomberg, and there were a number of Nobel laureates on this panel. And you can still get this study. It's downloaded as a PDF. And the study, I'm paraphrasing, but it basically said, the technology to shoot down, to defend the country strategically against nuclear missile attack by directed energy, lasers, microwaves, particle beams, the technology to do that would be 2 or 3 orders of magnitude beyond what we know how to do in the 1980s. And it's so far beyond what we know how to do, we can't even lay out a development program that makes any sense and be able to predict how many decades it's going to take or how many hundreds of billions of dollars it's going to cost or whether it's going to be successful at all. So that took the gas out of lasers for directed energy for strategic defense and microwaves and particle beams. That 1987 report. Now, there's one more. The last gasp of laser weapons for strategic defense was this alpha laser. You see that here, and you're going to see another picture of it, which the Strategic Defense Initiative Organization, SDIO, inherited from DARPA. I'm going to say a little bit more about that in a couple of slides. Now, why were these chemical lasers, why did people get so excited about this in the 70s and 80s? They do efficiently convert chemical energy into light. I draw your attention that, for example, the hydrogen fluoride, which is only in space because it doesn't go through the air, and the deuterium fluoride, which is in the air, does go through the air. They can store in the chemical bonds some 20 to 30 megajoules per kilogram of the chemicals. That's a lot. You're going to see that for the electric lasers today, those lithium batteries, you know what they store? They store less than 0.7 megajoules per kilogram. And that's the best we got for batteries. So they're very efficient at storing energy. And then you do a chemical reaction for the hydrogen fluoride. It literally was a combustion. And you have, at the end of that combustion, for a few milliseconds, you have something that's not in local thermodynamic equilibrium. You end up with the hydrogen fluoride or deuterium fluoride in an excited state. And as it cascades down, you get it to laze. But to get it to laze, you need this giant building full of laser. That was a megawatt class laser. And you need this giant beam director. It's about 1.5 meter diameter beam director telescope, and there's your 6-foot man sitting next to it. And you can imagine, putting this on a surface ship? Eventually the Navy decided this doesn't make any sense. We can't, and also we really don't want tons of hydrogen and tons of fluorine. Hydrogen is explosive and fluorine is poisonous. We really don't want that on a ship. So this got shut down. The next chemical laser that came along that was very popular was called this oxygen iodine laser. It's a different kind of reaction. It's not really combustion, but it can produce 3 or 4 megajoules per kilogram of chemicals, which is pretty good. And it very efficiently converts the energy into an excited state of iodine, and then that you can make it laze. It's shortwave infrared, and it goes through the air. And the Air Force had a program, first the Air Force, and then it was Missile Defense Agency, to put this in a 747 aircraft. And the purpose was to shoot down tactical missiles. Not nuclear-armed ballistic missiles, but things like Scuds. This came along after the 1991 war in the Middle East. So this laser and all its control systems and optics and everything else filled up this 747. And this, after it shot down a couple of short-range sounding rockets, it was decided this really didn't make sense as a weapon system, and this program was terminated. Okay. Now, I want to show you about that alpha laser. This was going to be in space. This was the gain generator. Again, hydrogen fluoride would flow out radially through this gain generator in combustion, and optics would be at the two ends and make the beams go back and forth, and you'd get a laser beam. Well, that's the gain generator. That's what the infrastructure was at the Capistrano test site to operate this laser. There's acres and acres and hundreds of millions of dollars of infrastructure to handle the chemicals and do the pressure recovery and all of this to make it work. And then someday that was supposed to be a laser weapon in space. This was the first directed energy program that I worked on. Okay, so I'm entitled to have an opinion about it. Okay, what do you think? What do you think? Okay, that somehow all of that was going to get packaged into a satellite. Okay? And this was a serious program. Went on for many years. Okay, what happens after that? Well, then the emphasis goes to tactical defense. People finally accepted that we're not ready to shoot down nuclear ballistic missiles with lasers or microwaves or particle beams, but we could maybe do this tactical defense and offense. So there actually was something called the THEL, tactical high energy laser, which was deuterium fluoride chemical laser. Again, a building full of laser. Somewhat smaller beam director, and it shot down mortar shells and artillery shells and so on. And people thought maybe I could put this into a bunch of trucks, truck it around. Again, the idea of trucking around hydrogen gas and fluorine gas really didn't make a lot of sense. But all this time, commercial industry was working on electrically pumped solid state lasers, crystal slabs, optical fibers, other laser media. And the breakthrough for this stuff really came in around 2009, 2010. A 100 kilowatt, totally electrically pumped solid state laser was produced by two different contractors, sort of the size of an industrial kitchen refrigerator. Okay. And then the laser world was off to the races with these electrically pumped technologies. Some highlights. In 2019, an electrically pumped laser, 150 kilowatts, was put on a ship, the USS Portland, and this is an infrared picture of it shooting down a drone. The laser was on the bow of the ship and the foredeck. Okay, and another number of other highlights here of electrically pumped lasers. The development of these diode pumped solid state lasers really opened the door for actual weapons that weren't just demonstrators, that weren't just laboratory things, but actually got out in the field and you could really see how you could use these as weapons of war. The first one that was actually put in the field is called the LAWS, Laser Weapon System. It was put on the USS Ponce, a destroyer. It was 30 kilowatts, diode pump optical fibers. It was deployed on the ship from 2014 to 2017. And the reason why the whole thing was such a breakthrough is because once you have these electrically pumped solid state devices, they're much smaller, they're much lower size, much lower weight than these humongous, building filling chemical lasers that I showed you pictures of, were 747 aircraft filling lasers. So now you can think about actually putting these in the field, putting them on vehicles, making them transportable, making them mobile. Okay? I will say there are some costs. If it's an electrically pumped laser, unlike something that gets its energy from a chemical reaction, you need a separate power source. Secondly, and the power source, is you put the power into batteries, and the batteries only store a fraction of a megajoule per kilogram. So you need a lot of batteries to equal the power and the energy of those chemical lasers. And furthermore, I got to say, the efficiency, most of that chemical energy can get converted into light in those old chemical lasers. But for these electrically pumped things, 2/3 or more of the energy ends up as waste heat. So you got to cool it, and then it's all that energy you stored in those batteries, 2/3 of that just is heat, and you got to throw it away. So there are costs to this, and we'll come back to that later when we talk about limitations. There are today, acknowledged by the DoD, 22 directed energy weapons that are deployed. They're all electrically driven in some way. They're mostly for defense against soft targets, things like drones, shooting down drones, exploding artillery shells in flight. And here we list, we give the names of them. We're going to show you pictures of most of these in some later view graphs. These are all at the, I liken this stuff to the air power, aircraft as weapons in 1914. They were balsa wood and cloth stretched over balsa wood frames, and they were biplanes. And they weren't really very dangerous. They mostly were an annoyance compared to the stuff on the ground, okay, of artillery and tanks and poison gas. Those biplanes were not very serious as weapons. This stuff is just the entry level. What's coming in the future for the harder targets on more mobile platforms will be will go after targets like cruise missiles, maybe eventually fixed-wing aircraft. They will be, they'll have higher power, they'll have higher efficiency. Hopefully they'll have better energy storage and heat management technology. And they will be integrated into and complement all the other stuff that's out there, kinetic weapons, electronic warfare, and so on. That's not there today, but that's what we will see coming, and we'll have more to say about this in additional slides. Now, I just want to say a few words more about the physics of this. What are these diode pump lasers? How do they work? What's the physics of them? There are, for the diodes, there's two ways to, a single diode, by the way, a single fiber, a single laser fiber that's pumped by laser diodes can produce 1 or 2 or maybe with exquisite engineering up to 3 kilowatts in a single fiber beam. That's not enough to be a weapon. 3 kilowatts in a single beam that's basically diffraction limited, that you can focus on a distant target. So how do you make things that are 50 kilowatts, 100, multi-hundreds of kilowatts? You have to combine many fibers. One way to combine them is spectrally. It's sort of like working a prism or a grating backwards. Many fibers, they all have slightly different wavelengths, and when they go through the combining optics, each color comes out at a different angle, and then all those different angles get combined into a final, the same angle, and all those different colors get overlapped. So now if you have a 2 kilowatt in a fiber and you have 150 fibers, you can have a 300 kilowatt laser. I'm going to show you that in a couple of slides. Another way to do this is to coherently combine them. You take many, many fibers and you make a phased array. And each one, a fiber might have 1 or 2 or 3 kilowatts, but they're all, spatially, it's all phased up, so you can focus it all to a single spot in the far field as if it was all in a single beam. And this kind of laser has also been demonstrated. There is another type called the distributed gain, which uses slabs of crystals. And you pump them with laser diodes, and every slab adds a certain amount of power. And you can have multiple modules and lots of laser slabs and get the power up to the multi-hundred kilowatt level. This has been demonstrated. And finally, there's something called the diode pumped alkali laser. Alkali atoms, you can pump them with laser diodes and pump them to an excited state, which then relaxes with very little loss of energy to a state, another excited state that's just a little bit below the one that's pumped by the diode, and then it lasers down. And these, depending on the alkali atom, can work from 700 to 800 nanometers, just outside the visual range, just outside visible light. And this has also been demonstrated. And I just want to show you some photographs before I get off the stage and give this back to my my colleague, Dr. Trebes. I said these really exist. Well, here's a 300 kilowatt spectrally combined fiber laser demonstrated by Lockheed Martin Corporation in 2022. 300 kilowatts average power. Also demonstrated is a 300 kilowatt coherently combined fiber laser demonstrated by a different contractor, Enlight, in 2023. And here you see you don't have to count all the little dots, I'll tell you. There are 151 fibers there. 151 in this array, which when it gets all phased up, makes one spot in the far field. Okay, and a very good beam quality. This is a distributed gain laser. General Atomics produced a 300 kilowatt class distributed gain laser. It'll fit on a not very large optical table. You put a box around it. It makes a nice package. And then finally, the diode pumped alkali laser is a laboratory device. I can't say the power, but Lawrence Livermore National Lab has been leading research on that in this country. So we already have in laboratories 300 kilowatt average power HELs. There are some lower power HELs that are actually in armored vehicles and on ships at the tens of kilowatts to 50, 60 kilowatts. But for higher power, we're at the 300 kilowatt level, and these contractors are moving on to 500 kilowatt and 1 megawatt average power, scaling up the power. Okay. Again, I want you to, this is a laboratory, okay? It's not a whole building. Remember, you saw that enormous building or a 747 filled with stuff to be a megawatt class chemical laser. These are much more compact. Now, somewhere there's a power supply and somewhere there's a bunch of a chiller to take the heat out. Got to have that somewhere. But these seem to be much more compact than what was a generation or two back in the 80s and 90s. Now, I don't want to oversell here. Every laser went through this process of, rapid growth in power. From the first thing somebody did in the lab, the CO2 lasers went up to the megawatt class, then the HFDF, then the chemical oxygen iodine went to the megawatt class. Now we have the solid state lasers and the DPAL, the electrically pumped, and they're up in the multi-hundred kilowatts, hopefully soon to be up in the megawatt class. We haven't hit the limit of those electrically pumped lasers, but there will be a limit. We'll hit it. We want to find out where it is. It's not going to go up. They all have their day and they all have their limits. We don't know where the limits are, but the history of this has been everybody hit their limit. What really prevented these other things from putting weapons in the field is their size, their weight, and all the other operational issues that impeded that. People they didn't want to have explosive, poisonous chemicals or, a 747 coil laser orbiting over the Persian Gulf is a big fat target. Okay, operationally, it was just deemed this doesn't make sense. I think. Yes, my get off the stage one for a while is that I've talked a lot about the lasers, the power source. We'll see something about the microwaves soon. A weapon is much more than a power source. And these directed energy weapons are much more than just a big laser. And I call your attention, we've got the red boxes. Here's the laser source. And there's lots of interesting physics in making more powerful lasers and making them more efficient and making them more compact. But to make a weapon, you've got to have, you got to have that power. You've got to have a cooling, and that's where 2/3 of the energy is and a lot of the weight. And then you've got to have this beam control. You've got to track the target, identify the target, aim at the target, correct for atmospheric turbulence, do fire control, all kinds of other functions have to be done. And each of these 4 boxes is a comparable size and cost and complexity of making a weapon. And in fact, a lot of what needs to be done to get these in the field isn't anymore on the laser source. It's on making the power and cooling smaller and more efficient and getting this beam control to be more robust, more rugged, work in the field and work in more environments. Okay. Now, to you, Jim.
Yep. Before I get into the physics limits, I want to say one thing. In 2014, when the USS Ponce got its 30 kilowatt laser, that was a remarkable event because it showed that a laser could actually provide real military value to a ship and operate on a ship and be operated by regular sea personnel, not conehead scientists and engineers. And so it really opened everyone's eyes about the potential. And we're fortunate we actually have one of the key people who made that happen, Tom Shrimp, who's sitting out here in the audience. Really was one of the key people making that happen. So physics limits what you can do. There's no free lunch here. Beam control is critical. I've got to propagate a laser beam from my source through the beam director to eventually get to a target. The atmosphere is cruel. I've got to get to a small spot. There's atmospheric turbulence that's going to screw that up. There's what's called thermal blooming. These are intense lasers. They heat the air. They typically have a Gaussian-like beam, which means the center of the beam is more intense than the fringes, which means the heating is more in the center of the beam, which means it's going to drive the density of the air down in the center compared to the fringes of the beam, which means I have a negative lens, because the index is going to go down with the density, the index of refraction, which will cause the beam to diverge. So I have to keep the power level below a certain amount to avoid thermal blooming. And you do that by making the beam bigger and bigger in diameter, which means a bigger and bigger beam director, which means more cost, more size, more weight. These things grow. I can do some things with adaptive optics. Adaptive optics is a deformable mirror where I have a large number of actuators which can locally bend the mirror slightly to try to compensate for distortions, and there are multiple lasers in the laser weapon to try to measure what those corrections need to be and make them happen. If I'm going to a pulse laser, I get stimulated Raman scattering, where the photons are now interacting with the molecular transitions in the atmosphere. And if I get above a certain power level, I start to scatter a lot, and so I get no free lunch with a pulse laser. And I get self-focusing, where the electric field of the laser beam can actually drive the index in a nonlinear way to cause the beam to focus. And so again, there are limits there. Microwaves also don't get a free lunch. They propagate pretty well. An antenna determines their beam profile, but I can only put so much power through a spot in the air without causing air breakdown. I can do things like take a balloon with helium in it and put it right in front of the antenna to get me a little bit of margin, but I can only do so much. And so megawatts per centimeter squared, and I start to break down the air. And so a cure is to go to a bigger and bigger antenna. But bigger antennas, bigger weight, bigger cost, bigger size, bigger problems. Again, no free lunch. And then the directed energy weapon is in what's called a kill chain. It's not just, once you get the weapon done, there's all the rest that has to happen before it can actually get used. And so in this case, we're considering the scenario of I'm going to engage a cruise missile with a laser. So the first thing that has to happen, well, you have to be in the right place at the right time, so that your laser has to be somewhere. And but the cruise missile has to get detected by some kind of radar. It might be on the ground, it might be on a ship, it might be in an airplane, but there's some long-range radar that identifies and begins to track. That information gets sent to a command and control center, where decisions are starting to be made. Is this something we want to engage? If so, with what? There are a lot of options. What kind of missile do I want to use? Do I want to use a microwave? Do I want to use electronic warfare? Do I want to use a laser? If I use a missile, once the missile's gone, I might not have a replacement for it. So magazine depth gets folded in here. So a lot of decision making. The data is also going to a local radar that's going to get the handoff of the track and start to provide a better, more accurate track. All of this data and decision making then goes to the laser weapons system. And then the laser engagement sequence begins here. And so I have to optically acquire with my beam director. It's a fantastic telescope. This is a great thing, and it's great for reconnaissance and observation when you're not zapping things. I have to acquire it. I begin to track the target optically. I'm going to center on it. I'm going to put a pointer laser onto there. I'm going to identify what the target is. I'm going to pick an aim point, and we'll talk about aim points here in a few minutes. Of what I'm going to shoot at. I'm going to begin to do my atmospheric corrections with my adaptive optics. I'm going to get a very fine track, precision track going, and then I'm going to turn my laser on. And I might actually turn the laser on only for a few seconds, but this overall process could take 10 seconds. And so again, there's no free lunch. I don't get to go zap, 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 zap. It's zap. It takes time. And then after I've done all that, what did I do? And kill assessment's actually a really tough problem. If I hit the thing, put a hole in it, so what? And we'll get to that of what really constitutes a kill and how I do it. But you must fit into a kill chain with all the other weapon systems going on. And all that has to be integrated in, and that is a real severe challenge. It's also a challenge for all the other kinds of weapons as well. In today's multi-domain, multi-mode, multi-level, multi-everything warfare, it is a complicated mess. Laser weapons attack, materiel, structures, sensors, controls. There's two types of kill we talk about: system kill, and Tom's favorite phrase for that is flaming wreckage. That's rarely achieved, by the way. And then there's mission kill, which means you do enough damage to prevent the mission from happening, i.e. you damage a cruise missile enough that it's going to miss its target. And that's called a mission kill. And lasers are typically, and microwave weapons are typically going to do mission kills, almost always. And so I have on here the freshman physics problem down here. So we'll take a 300 kilowatt laser, which is what industry can readily produce now, 1 micron. 50 centimeter diameter beam director is sort of, the Army's building some. There's some smaller ones, there's some bigger ones, but that's sort of a good number. Shoot it about 20 kilometers out. We have a spec called the bucket. The bucket is for a reasonably well-behaved beam, reasonably Gaussian. It's 3 times the wavelengths times the range divided by the aperture size. 2/3 of the laser power is inside that bucket. And so that's going to give us a spot size. I can put enough power in that bucket, if I'm shooting an aluminum target, that I can blast through a centimeter of aluminum, and that sort of mocks up a thin aluminum skin and then an electronic control box inside and the circuit boards. I can get through that in 1.5 seconds with a 12 centimeter hole. So it's an impressive thing you can do, and you throw in and add another second because there's all sorts of other bad things that will happen. So in about 2.5 seconds, I can do something. But does it matter? And so holes are not the game here. So I have two images from World War II. These aircraft made it back. They have lots of damage, and you can pick your favorite air war: World War I, World War II, Vietnam, Gulf War I, Gulf War II, Korea. There's lots of great pictures of what came back. Israel had an F-15 come back on one wing. Literally, it did. It's amazing. And so making a hole is not enough. I got to make a hole where it matters. I'm going to skip to this and then come back to that. And so how do I do that? How do I know where it matters? And so I'm going to pick a target that I'm interested in. And so there are lots of targets, and so you'll have to do this a lot of times. And so we'll say a cruise missile. I'm going to gather all the information, all the intelligence I can on that cruise missile. And there'll be gaps, but there are design rules for cruise missiles. Cruise missiles don't have a free lunch either. It's going to have to fit in a launch tube. It has to fly a certain way. It constrains their design and how they're built. I need to know what materials. I need to know the structures. I need to know the functions. And then I do a failure analysis. If I break something on this cruise missile, what happens? Maybe nothing, maybe catastrophic. And I want to find the easiest spots to cause the most damage as fast as possible. And so I do this analysis. I do a lot of modeling and simulation, and I find 4 or 5 places I think I can really break this without having as maximum power required. And then I start irradiating test samples for the materials, laboratory tests, done all the modeling and simulation. Is any of it right? I got to get this right. And so you validate your modeling. And then I move into subsystems and components. And if I'm lucky, I can actually get the real ones. And if I'm not, I have to use a surrogate, and maybe I have to build something. And you irradiate those. And then I have to go to field tests. And if I'm lucky, I can get the real thing. Sometimes we can get adversary systems. You can buy them sometimes. Sometimes not, and you have to use a surrogate. And we do that. And then you fire at the real thing and you see what happens. And then you analyze all the results. And the kind of things you're shooting at are the guidance system, the control servos, the control surfaces, the engine, the fuel tank. The warhead actually turns out to be really tough. We actually tried that. It's one, contained inside a steel case, and two, it wants to deflagrate rather than explode, and it's a high volume. It's a big thing, so the surface area to volume ratio is wrong, and so it didn't do much. It doesn't go boom. You'd love it to go boom, but it doesn't ignite. We did try that, modeled it to death, and still couldn't get it to work. So you take all these results and you construct what's called a vulnerability module, which is a software package, which amazingly enough is standard across the entire Defense Department. You know, miracles have occurred. And so you don't want a sergeant or a seaman trying to do physics calculations on the fly with an inbound cruise missile coming at them. So all of that is in the vulnerability module, which goes into the fire control. And so there's a person operating the system who has their finger on the button, but the software is saying you want to go for this spot for this many seconds, and it corrects for the angle, and it's got all that in there. And so we're trying to make sure that the corporal is not a PhD physicist and doesn't have a giant computer next to them. And so that's what's done. So here's a test coupon getting zapped. And then this is a Lockheed 70 kilowatt system shooting at a drone, a jet-powered drone. The bright spot is where the laser's hitting it. This is an IR picture of the beam going to hit that spot. And then this is done at White Sands. You're not allowed to, burning wreckage is hard to come by because of the safety rules. And so in this case, they're attempting to damage, and they have fatally damaged the guidance system, which forces the flight termination system to go into effect, which means it pops a parachute and the engine cuts out. And so you don't get flaming wreckage, but they did kill the guidance system. Let me go back. There's continuous wave lasers versus pulse lasers. Pulse lasers, 10 nanoseconds, microseconds, they damage by ablating material, causing spallation where you're hitting the outside surface and you're causing the inside surface to flake off and spray inside, creating holes, creating cracks, which lets the air drag do their thing to rip the aircraft apart, shattering of components, disruption of flows. You can go to very short pulse lasers, picosecond, tens of picosecond lasers. You can get RF effects, plasma effects, which can screw up sensors and electronics. And then we're trying to understand right now the trade-offs. So it's all about lethality. And so if the lethality effect from a pulse laser is significantly better than from a CW laser, I, in principle, could go with a smaller, lighter weight, but probably more complex laser. And so there's a trade. Again, there's no free lunch here. I get different effects caused by different systems, but I'm not sure which one's best. And I'll say we haven't worked that out yet. Work in progress. Microwaves, again, you're trying to produce, taking a microwave beam, irradiating the target, trying to get inside it, create a high electric field, drive currents that either overload a circuit or cause it to change or malfunction. You can get a 100-meter spot at a decent range with a gigawatt of power. There's two forms of attack. One is called the front door. If I have a radar receiver, or the radar's got a big antenna, if I've got a radio receiver, it's got a big antenna, I can shoot down the antenna. The antenna gives me significant gain, a lot of gain, and it minimizes the amount of power I need. But I need to know a lot about the target because I need to know what wavelength I need to be at with my microwaves, and I need to understand some of the electronics inside, and I'll get to that in a second. And then there's what's called the backdoor attack. Every missile has cracks, gaps, seams, holes that microwaves can go through, get into. And so I can get microwave power in, but then it's got to get inside a control box, which also has gaps and seams and holes. And so the microwaves have to rattle around inside, and then that becomes a low reliability because I don't know necessarily how well it will rattle around inside. And then it turns out variations in construction matter and the age of systems matter. Gaps grow, gaps shrink. I've seen variations on U.S. systems which give you remarkably different answers within their normal manufacturing spec. And so HPM, high power microwave lethality, is hard to model and hard to get right. So you have to do a lot of experimentation. Here schematically, you have a gigawatt propagating. It's X-band or S-band, which is gigahertz to of order 10 gigahertz. You're producing about 100 volts per centimeter at an antenna. It's flowing through the antenna into, you want to get to what's called the low noise amplifier, the sensitive part of the electronics of the system you're trying to kill. The designers of these systems don't want you to do that, and they also don't want things like lightning putting RF in there either. And so they build limiters, which can be as simple as a pin diode or be very, very sophisticated. And the limiter is designed to make sure your power doesn't go through, but their power does. And so you have to either figure out how to overcome their limiter, and that's a game everyone plays against each other. How much power do you have to put in the limiter? I have some Chinese numbers. For a low noise amplifier, it's tens of watts. And then the kind of damage it does, here's a field effect transistor inside the reference is our favorite friends, the Chinese. We feel free to use their data. You can zap a field effect transistor. I'm shameless about my use of Chinese data. Back to my colleague.
Okay, now, despite all the limitations, despite all the issues that we need a power source and we need batteries and we need cooling and yada, 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 we have finally deployed directed energy weapons as defensive weapons against soft and slow targets like drones, rubber, Zodiac boats, blinding of sensors, unguided rockets, artillery mortar. And here I'm showing you some of these. The Navy has 8 ships with this Odin system, optical dazzling interdictor Navy is what they call it. It's low power lasers. These are not high energy lasers. They're low power, but you point it right into the optical front end of a sensor on a UAV or a drone or something, and it will dazzle it at the very least, or it could permanently damage it. There are 8 ships that have these systems on there. The Navy has an actual HEL weapon called Helios, 60 kilowatt class laser, and that's what it looks like. It's on a Arleigh Burke DDG destroyer. And it is designed to, again, bring down drones, disable or sink these little rubber Zodiac boats, so-called fast inshore attack craft, FIACs. The Army has, they have a program called Mobile Short Range Air Defense, MSHORAD. And there's a kinetic system which uses basically Stinger missiles to shoot down rockets, artilleries, mortars, drones, that sort of thing. But they have a directed energy MSHORAD. And there are 50 kilowatt class lasers, 4 of them in Stryker armored vehicles. It's a mobile system. And here you get a little bit of a close-up. The thing sticking up high is a radar for acquiring targets. The HEL is this ball that's actually closed up. That's clamshell opens up, and that's where the HEL beam comes out. This picture was taken at Fort Sill, Oklahoma. These systems have now been shipped out to the Middle East for being exercised in the Middle East theater, and we'll see how well they work in a sandy, dusty desert environment, and we'll see how they do. There's something called a compact laser weapon system the Marine has. It's sort of 5 kilowatt class. It's much smaller. They can carry it around and set it up. It's not on a vehicle, but it's easy to set it up for sort of perimeter defense against drones. There have been some somewhat higher tens of kilowatts put on these vehicles that are sort of like a stripped down Jeep. And again, you can see the ball thing on top. That's where the laser beam projector is, and therefore shooting down or disabling drones or blinding sensors. And there's also a microwave weapon called Thor, which is a high-power microwave system that has a range of, well, I won't say the range, but it's for knocking down drones. It'll zap the electronics of a drone, and the thing either loses ability to control itself or it reverts to some sort of safe state and goes back to mama, goes back home someplace, stops looking at you. There is development of direct energy weapons for the more stressing, the next level, which means cruise missiles. They go a lot faster. Subsonic cruise missiles will go Mach 0.8, 0.9. There's supersonic cruise missiles that in their final stage come in Mach 2 to Mach 3. The Army has a program, indirect fire protection. That's going to use 300 kilowatt class lasers like those electric lasers I showed you in an earlier slide. This is not the IFPC-HEL, the 300 kilowatt. This is a photograph of an earlier system, but the IFPC-HEL will fit into a similar size vehicle, a truck basically. It's not to shoot on the move, it's to go to some place that needs to be defended against land attack cruise missiles, and as part of a kill chain would shoot them down. There's a high power microwave version, which the Army is building, and expected in delivery in this fiscal year, that uses high power microwaves. And I believe this is really a front door. It's to disable the sensors, the radar seekers of these kind of weapons. The Air Force Research Lab has been working on a device, a system called Chimera. This is an experiment. It's not intended to be a final system, but this Chimera is a high power microwave, again, to be a front door attack to defend against cruise missiles at long range. Again, I can't say the range, but it's quite a long range. Notice it has this big antenna. And then there's this spherical thing. The beam comes out, and then goes into this ball kind of, and then off the antenna and goes to the target. What is that big ball there? That's a bag, a gas bag of sulfur hexafluoride. And the beam goes through that. It doesn't cause breakdown of the sulfur hexafluoride, and it expands. And when it finally gets out of that outside that bag, the radio frequency energy or power level or flux level is below the air breakdown. So now it can go out into the air and into the antenna. The follow-on to that is a device that'll be called Defend, and that is going to be look more like something that could be deployed to actually defend against these long-range cruise missiles. Finally, so now we've had the Army, and this is, again, for base defense, Air Force against cruise missiles. And here's the Air Force on an airplane. This is the first picture we've shown of these electric lasers on an aircraft. The Special Operations Command, SOCOM, had this program called Airborne High Energy Laser, AHEL. It's going to be 60 kilowatts, roll on, roll off, to shoot at things on the ground. And this would be an offensive directed energy weapon. And the program was just killed. It was zeroed out in the budget, and SOCOM has declared this week, I think, did a press release saying, we're done. If anybody else wants this thing, it's all palletized, the laser's all built, the beam director's all built, but we're not going to fly it on a C-130. If you want it, you can have it. So if you know anybody that wants one, it's available. Now, other countries are developing the same technologies or similar technologies, and for similar kinds of missions. The Russians have this laser dazzler that they call Peresvet, and it's designed to shine up into the sky, into outer space. It's designed to dazzle and blind sensors that are up there looking down on them. They don't want anybody looking down on them. And they have deployed, there are multiples of these, and they are at various facilities, military facilities in Russia. They have a microwave weapon. Here's a photograph of one. They used to have, I think this has been retired, they had an airborne laser. I believe this was CO2 laser. As far as we know, this is, they don't play with it anymore, but they had it. The Chinese have a laser on a ship, and here's the beam director for that laser. The Chinese are selling a ground-based system they call the Silent Hunter on a vehicle, sort of like that DEM SHORAD. It's that kind of tens of kilowatt class, we believe, for shooting down drones. It's for sale. Interestingly enough, the Chinese have this laser rifle. What is this? Well, this is not like the phaser in Star Trek where you'll zap somebody and they'll disintegrate. It's not that. But this certainly will blind you if you don't have protective eyewear, and it will blind other sensors, night vision devices, cameras, and so on. And it is, handheld. The UK has a device called the Dragonfire. This is a demonstrator. It's not to be a deployed weapon, but they have fired it at test ranges. Again, electrically powered fiber laser. And even the Turkish military has this laser weapon on a truck, and this is again in the tens of kilowatt class to shoot down drones. So everybody's in the game, and there are many other countries. Israel is developing something called the Iron Beam. They had their Iron Dome, which is a kinetic defensive weapon to shoot down unguided rockets and artillery and mortar. Each of those every round in the Iron Beam is $50,000 to $100,000. Iron Dome rather is $50,000 to $100,000 per round. Okay, and they're shooting down Katyusha rockets that cost a few $1,000s, or artillery shells that cost a few $100s a round, or drones that might be a few $1,000s. So it's not a great cost exchange. So they are now investing in this thing they call Iron Beam. They had a prototype that was a lower power. That's what these photographs are. It's a lower power one. It's actually a pretty small device that's up here on this tower. This was for prototype testing. They were very happy with how well it worked. And now they are developing 100 kilowatt class, and it will be deployed in 2025, they say, if they stay on schedule. So they're committed to doing this. They want the cost exchange. They think because of the cost exchange, they need to not just be relying on the Iron Dome, which they would presumably use against the more expensive targets, and the cheaper, easier stuff to knock down, they would like the Iron Beam. And now, back.
That's right. So I'm going to come back to interest has never been higher in directed energy weapons, and it's because of the large number of drones, the large number of rockets, the large number of missiles that are showing up from a wide range of countries in the world. The Russians have copied the Iranian drone. Everybody's copying the Iranian drone, by the way. They have their own version they're using in the Ukraine. The U.S. has built a drone interceptor drone, and they're $250K a pop. It works, but it's expensive. And then here are the various Houthi missiles and on parade. Again, they have lots of them. I think Hezbollah has something like 120,000 rockets stored up in their inventory. So there's a lot of rockets out there. And so people are looking for deep magazine, rapid fire, low cost per shot, some kind of solution, because we cannot win the exchange firing multi-million-dollar missiles at $10,000 targets. So why not? Why aren't we doing that? That's the big question. It's really a confidence question. The warfighter does not believe. The technology is new. It's not proven. It has not been suitably ruggedized. We don't know the maintenance needs. We have seen maintenance problems with the operational demos. You have to, track much more accurately. You need a kill web that can support directed energy. And that has, you have to integrate into that. That's an added complexity. Weather's a factor, and we'll get to weather in a second. Countermeasures are an issue. The bad guys can build countermeasures to directed energy weapons. These things are expensive to buy. Laser weapon systems with everything, all the pieces and parts are expensive. As the joke is, it's low cost per shot after the first shot. There is a thin industrial base. This is a chicken and the egg problem. The major aerospace companies all can build these things, but they're set up to build one of a kind or two of a kind. Like Lockheed's building two IFPC Hell 300 kilowatt trucks for the Army. They are not set up to make 100 of them. They're set up to make two of them on a more leisurely time scale. If there was a large order, they would ramp up. but there's not a large industrial base because there is not a large order. The real net value of directed energy is just not proven. And when the Department of Defense looks at a threat, they look at all the possible ways of dealing with that threat. There's an analysis of alternatives. And you want many options. You do not want a single silver bullet. And directed energy has not reached the bar where it's, oh yeah, we got to do this. It's getting there, but it's not there. And the bottom line is the military trust factor is just, it hasn't been earned yet. Weather. Everybody always asks us about weather. And the answer is it's a problem. Clouds, rain, particulates, you'll get, thermal blooming effects, scattering effects, nonlinear problems. When we evaluate laser weapons systems, there's a lot of modeling that goes on. The first thing you do is under ideal conditions, what can you do? And then the next thing you do is we do it under average weather for wherever you're planning to use this thing. And then you look at the poor weather conditions. And so the people considering the use of the thing are given, this is the best it'll ever do, this is the likely worst, and this is what you're probably going to get. So we do worry about that. And then you have to understand all weapons systems have to deal with weather. It's very hard for anyone to fight with anything in a giant sandstorm or in the middle of a hurricane or dealing with tornadoes. Again, there are no silver bullets that punch through everything. And so weather is a factor. Radars and other sensors, optical sensors, infrared sensors, all of these things are affected by weather. And so everybody has to take weather into account, and we do as well. And there is some weather we cannot shoot through. If you get on an airplane and you get up high, life is a lot better, but we're not there yet. Every weapon has a countermeasure. For lasers, I can put smoke out. I can put particles in the air. I can use a narrow bandpass laser filter to protect a sensor from the wavelength of the laser. I can use reflective coatings. I can use decoys. I can put ablative material on there. I can spin the missile or the artillery shell and distribute the laser energy over 2 pi. I can go to high G maneuvering and high speed to make tracking harder. I can go after the kill chain. There's nothing like, killing the kill chain is a great thing. I can go kill the laser. There's a lot of things I can do. There are similar things for countermeasures. I can improve the seals and joints and the holes and feed-throughs. I can improve the limiters. I can go kill the kill chain. I can go kill the microwave weapon. I can do all of these things. But the countermeasures people also don't get a free lunch here. If I deploy countermeasures, I've got to do it at scale. I'm adding weight. I'm affecting performance. I'm adding cost. And so there are trade-offs. And then the directed energy weapons people will go, well, if I can change my pulse shape if I'm a pulse laser. I can dwell longer. I can focus tighter if I'm a CW laser. And so there are things you can do on either side. So there's a lot of trade-offs. But you have to worry about, if you're deploying directed energy weapons, there will be countermeasures.
Okay. So we've got these directed energy weapons, and now we've solved all these technical problems. They're smaller, they're more efficient. We have the power source, we have the cooling, we got the cost down. We understand, we're ready to respond to countermeasures. We got everything worked out. Everybody wants it. The Army, the Navy, the Air Force, the Marines, everybody wants it. Then you have to go through this. Okay? This is a real chart of the acquisition system for a program of record in the Department of Defense of the United States military. Okay? Imagine having to go through this mess, go through all of this through the normal system of developed requirements. And you have milestone, this has milestone A and milestone B and milestone C, and and this is competing against this new kind of weapon, which admittedly has uncertainties because it hasn't been in the field long enough for us to understand how it really compares with alternatives. So this is what, when you say, why isn't there more in there? Why isn't there more out there in the field? And why isn't more money being spent? the idea of going through this and being able to satisfy all of these processes and reviews and milestones and so on, and have the understanding and experience to be able to do that. Well, this is set up for the legacy systems and the things that people have been using for 100 years. Direct energy doesn't fit into that. Okay. But this is what you do in the Pentagon. This is why that 5-sided building is full of 25,000 people doing this kind of stuff. Okay. Okay, what does the future hold? The threats are going to get worse. The number of cruise missiles, drones, hypersonic missiles, all of that is going to grow. It's in the thousands to tens of thousands. Hezbollah's got reportedly 150 to 200,000 missiles it could launch over the northern border of Israel. The U.S. is going to face the same thing if it gets into a war, Middle East, Far East, wherever. Budgets are constrained, but the number of threats is going to grow, and there are these science and technology challenges. Today, we have technology that can deal with some of these threats, certainly the soft targets, the drones. We know that we have the technology to do that. We don't have much operational experience with it. It needs to be improved, made more rugged and so on, but that we can deal with. We expect we're on a trajectory for ground-based, to deploy more of these ground-based and ship-based high-power microwave and laser counter UAV, and eventually, a few years further down the road, counter cruise missiles. And I hope there'll be some airborne counter UAV, counter cruise missile systems coming along, although with the Air Force just canceling their one airborne laser weapon, the AHEL, the future is uncertain on that. What's very uncertain is whether we can reduce the size, weight, improve the efficiency, and reduce the cost to go after the very hard targets like hypersonic missiles and ballistic missiles, where the timeline is very short and the target is really hard and resistant to, and it's especially hardened against these kind of threats. So looking at the crystal ball, maybe we get to this big laser on a UAV, don't know. But now we have a debate because we have different points of view about what the future is going to hold. So we'll debate a few issues and then we'll open it up for questions.
So you've claimed we need a new agency to make directed energy weapons happen. A crazy idea if ever I heard one. So let's hear your story.
Well, I don't claim that we need a single agency in the Pentagon that does all directed energy weapons. I think each military service, if they actually want to use directed energy weapons, they need to create a very mission-oriented group inside their service that is dedicated just to building these weapons, getting them in the field, and getting experience on them. And I think if you look at the history of revolutionary advances in these war machines, if you will, most of the time what you find is successful. It's some small dedicated group inside military service that has assured funding and it has one mission to do one technical advance and get it in the field. You could say the Manhattan Project, which was an example of that. Certainly then Captain Rickover and getting nuclear power on submarines was an example of that. I would say that building stealth for the Air Force was an example of that. Most of the rest of the Pentagon didn't know what was going on there. I could find example after example. When Sputnik was launched in 1957, President Eisenhower didn't shove money into all the research labs of the Army, Navy, Air Force, but he created DARPA. He said, I'm going to create a new agency, and their only mission is to maintain technological superiority. And that's all they're supposed to worry about. And it was a very successful model. So when I look at what's going on today, I think the Army has been very successful with its so-called RCTO, Rapid Capabilities and Critical Technologies Office, RCCTO, and they were told to do directed energy, hypersonics, and I think space. I would say they need to change that and make a part of RCTO that just deals with directed energy. But at least RICTO, which was very focused on those technologies, got those 4 weapons on the Stryker vehicles. It's got that 300 kilowatt it's going to put on a truck. They've made incredible progress compared to, I may hurt feelings of some veterans here, but the Air Force, what's the Air Force got?
Nothing.
Nothing, okay? And because it's directed energy work is all being done by Air Force Research Laboratory. It's a research laboratory. They have great technology. They have brilliant people. They don't build weapons. They don't have the mission to get weapons out in the field and get experience with that. The Navy is somewhere in between. It's got the Naval Surface Warfare Center in Dahlgren Division that did the Odins and did the Helios. That's great. But again, the Naval Surface Warfare Center deals with all surface warfare weapons, okay? I wish that the Navy would create an isolated part and say, all you guys are going to do, if I hear the Pac Fleet 3-star admiral who's in charge of all surface weapons of our Navy in the Pacific saying, I want more directed energy. I got to accelerate this. I want this on my ships. Well, he should go and say Naval Surface Warfare Center, Dahlgren Division, needs a separate part that only builds me my directed energy weapons. Doesn't worry about big guns, doesn't worry about, vertical launch systems, doesn't worry about railguns. It just does this directed energy stuff. It focuses on that. I think the Navy would get more done. So prove me wrong.
I'm gonna. No, so what we're doing now doesn't work. I claim it doesn't work. It's not working. If the services really had focus centers and they had 4-star sustained, not personality driven, but sustained support.
Yeah. And money.
That would work. And so I have mixed feelings about an independent agency. Manhattan Project is maybe the most stunning success in developing the atom bomb. DARPA is clearly a success. I mean, one of the key missions for DARPA in its inception was to make spy satellites happen, and they did. And then they handed that off, the creation of yet another new agency, the National Reconnaissance Office, and then the Air Force created Space and Missile Systems Center to do their satellites. And then they evolved into, I'll call, steady state behavior. And the Defense Department recently created the Space Development Agency
to break through all of that.
Because they were missing the revolution in both satellite technology and launch technology that's exploded across the world, and the SDA is taking advantage of that. So specialty agencies may have a lifetime. And in fact, missile defense is an example where SDIO was created to be a special agency to make that happen, which evolved into BMDO, Ballistic Missile Defense Organization, which evolved into Missile Defense Agency, which has
ponderous bureaucracy,
which has very mixed results on directed energy. In fact, Tom and I are helping them reconstitute their directed energy program as we speak. And so these things have mixed results. So if you had specialty focus organizations within the services, and I think it has to be within the services, and you had the Secretary of Defense and the Deputy Secretary of Defense and the Joint Chiefs and the Congress, and especially the Congress, dedicating money and telling the services they had to do this and they can't just go spend it on anything they want, you could make that work. And so I would support a specialty organization with those constraints. But just creating a new organization, I think, hurts you. And when you do create a new organization, it's very hard to find the right people.
Yeah.
And then once you do, it's very hard to keep them. And then new organizations have a terrible time trying to figure out how to actually place a contract. And so standing up a new entity can cost you dearly in time. And so we need to get stuff moving. So a service-based center with Congress breathing down their neck, I would support.
Mm-hmm.
So I agree that we're not that far apart.
You got to have the right. First of all, you've got to have very high level support. The head of the commanding, the chief of staff of the Army's got to support this in the Army. The chief of naval operations would have to support this in the Navy. The chief of staff of the Air Force would have to support it in the Air Force. And then you've got to have the right kind of people run this. It's got to be people who they know they're going to become pariahs in their service. They have to they have to be successful at getting this stuff built and out in the field, because if they aren't, their career is over inside their service because they've alienated everybody else. So you need it takes a certain type of individual. Rickover was that kind, was fantastically successful. General Schriever in the Air Force got ICBMs to work for the Air Force, incredibly successful. We could, but these are rare. You get the wrong person in that situation and it all just turns to mush. So I agree.
The other second topic we want to talk about is ballistic missile and hypersonic missiles. What's it take? Tom and I both agree we're not ready now. And I think we're probably in pretty much agreement on what needs to happen, but we'll see what happens here. I think you can't wait. You need a hypersonic and ballistic missile lethality program today. We need to do a lot of parallel processing. You need major pushes on the size and weight and cost of components, especially power and cooling. We've got to shrink the size. We need to really start looking at kill webs, not just a kill chain, but the fully integrated story. Because when you finally have your microwave weapon or your laser weapon to put in, I don't want to spend 5 years or 10 years trying to figure out how to inject it into the kill web of systems. We need to parallel process. If we do that, you can, as fast as credibly possible, move forward to do something about hypersonics and ballistics. If we do this serial process one step at a time, we will never get there.
Well, we agree that we're not ready, and there's a lot that needs to be done. I'm skeptical that you can get the high level support needed and the money needed to go forward with that, when right now we can't even credibly shoot down a few subsonic cruise missiles, okay, even a few of them, okay, and have them integrated into these kill chains. That's part of the problem. It's still an enormous reach beyond what we know how to do. And I agree with that. There's a lot of underlying science that needs to be done, tests that need to be done, but to go forward, and say we now should start planning on and conceptualizing and working towards some specific vision of megawatt lasers on UAVs or in space or whatever. I can't see that people will believe it, because we can't yet credibly go at much softer targets, much easier targets. That's why I've advocated and wrote a plan that was in spirals, but it really envisioned going out another 15 or 20 years on those spirals, and that was aggressively. There was so much that would need to be done. I think we really differ on maybe the pace, how fast and how easy or how hard. I mean, I think it's hard just to get something like that IFPC Hell or IFPC HPM that the Army wants to put on a truck to just shoot down a couple of cruise missiles. The defending against, well, even it's with kinetic weapons or directed energy weapons, defending against hypersonic missiles coming in to kill you is an incredibly difficult technological problem. And the amount of time you have to do it is so short, and there's so many, we've got the fog of war and so many other confusing things going on. I'm skeptical. I don't see how you convince people to commit to doing that when we can't do it with much easier.
Well, the arguments, I agree, is going to be hard. But again, it's the pacing question.
So what's the third? Larry wants us to shut up so you get to the Q&A. So what's the third one?
Swarms are here today now. We actually have a focused agency. We have the Joint Capabilities Office for Counter UAS, and their existence in the Pentagon.
It's doing this right now.
It's doing that
somewhere
right now.
Lost.
So I have to give them credit. They've done a very good job of fielding operational demos of both directed energy and kinetic systems for dealing with swarms. They're getting them out, claws and the Hell Whiz, the 10 kilowatt, 20 kilowatt systems on vehicles or on tripods. That they help make that happen. But they haven't created programs of record and production and things like that. And so it's an agency that's hung up in literally that.
Yeah.
and you got to get past that. There are a lot of things one could do. The 50 kilowatt Army Striker system is very interesting for dealing with for drones. I think you could put a 100 kilowatt, 50 kilowatt, 100 kilowatt laser on a larger UAV at 10,000, 20,000 feet. You could do that pretty quickly, and then you'd have some reach. It would do wonders for the Ukraine. It would be vulnerable to air attack, so you're not going to go fly into Russia with it. It could do wonders for hovering over ships in the Red Sea and the Gulf. One could do that fairly quickly.
Let me jump in before Larry gives us the hook.
Yep.
I think that the counter drone, countering all these drones, which can come in the tens, come in the thousands in a swarm, this is the entry level thing, the first big app, if you will, in the Silicon Valley language for these directed energy weapons. And I don't even want to try to make them bigger or higher power. I just want to take what we have and start getting it out in the field and replicating it in making it at scale, because then we will rapidly learn how to improve it. But this is the thing that could get the industrial base to respond and invest. You know, it's that killer app that gets the system moving. And I would rather focus on the technology we have than even talk about, yeah, I'd love to see something on an airplane, you know, shooting down. But I don't want to be distracted by that. I see an opening here that the ships need it, air bases need it, army posts need it, maneuver troops need it. We have the level of technology today. Can't we just start building this at scale? So.
We had much better, more intense arguments in the Pentagon. So sorry.
Hi.
I have time for a few questions, not a lot of time, I believe.
My name is Scott Matthews. I am a member. I work for the U.S. Naval Research Laboratory, and so I have two questions for you guys that are from a naval point of view. The first is that we have this railgun, which, well, maybe it's not ready for prime time, is still a pretty cool kinetic system. Can you speak to how these laser-based systems would either compare, compete, or perhaps complement something like a railgun? And then my second question is, we also have nuclear-powered aircraft carriers. And on these aircraft carriers, we have very, very large nuclear power plants that can generate practically unlimited amounts of electricity. Is there a role or is there a place to put some of these laser-based weapons on carriers so that we don't need batteries?
Let me respond to that second question. Yes, there are big power plants on carriers, and on other ships there are big power plants, and the next generation ships that are in design will have big power plants. I will say that the ships aren't designed to deliver all of that megawatts to one tiny little place. I mean, the directed energy weapon and I've been on the ships where they've installed them, and it looks really big when it's sitting in a warehouse, and when it gets on the ship, it's just this little pimple on the foredeck. I mean, it's a tiny thing, and it wants to consume megawatts of electrical power, and it wants to generate megawatts of waste heat. And you would think, why is it so hard for a ship to get rid of the waste heat? You have the ocean, you have this biggest heat sink you can imagine. Well, the ship isn't designed to directly vent that heat to the ocean. It's not designed for that. So a lot of modification of the ship has to be done to do it. As far as aircraft carriers, I have a feeling, I've been on an aircraft carrier and there's no empty space. I don't know where I put anything like that. There's just no empty space. We've been on the destroyer Trebes that had the Helios laser, and they had to break that laser into about 8 different parts and stuff subsystems in different corners of different compartments to fit it onto the ship, because ship's not designed to take that. So the problem has a solution, but it's really requires a next generation of design.
So I looked at some of this. Navy ships have surplus cooling and surplus power, but it's distributed.
Yeah.
And as Tom said, in The Navy gets real upset if you run extension cords down the hallways. They don't like that, particularly when it's a megawatt. And so you can't get at it. So you're forced to use batteries and thermal reservoirs for cooling, batteries for power, and dealing with those on a longer time scale when they saturate or depleted. And so you wish you could. A carrier does have a lot of power and a lot of cooling available, but again, it's distributed. You can't get at it. You can't. I think you can put some lasers on a carrier. There's a question of whether that's the right place to put them. A head-on shot's hard to do. The nose is tough on a cruise missile. It's a lot better to have it on a destroyer taking a side shot to protect the carrier than the head-on. And so, I mean, the Navy asked me, can we put them on carriers? And I said, sure, but is that what you want to do? And that's I think it's an unresolved question. And so it might not be the best way to go at it. The Navy's doing their DDGX destroyer, which has enough cooling and enough power, centralized enough to support multiple lasers. That's the intent. I think it's 2033 now for the first one. And I've always,
And it's going to slip.
and I've already, when I was in the Pentagon, I always complained to the Navy, it will slip. And as soon as the budget gets too high, you'll cut out directed energy to save money. And so I'm worried that won't happen. But you need these things now. I even proposed sawing the truck off of the IFPC-L and just taking the box and bolting it to the ship. It made the Navy ill, but you could do it.
Like the laws was like that. It was just dropped onto the ponds.
And it may be that you have to do something like that. With the railgun, again, railgun is in the similar situation of there's no warfighter confidence. It has to get integrated into a kill web. It has an interesting electrical noise issue. You're firing a railgun. That's a giant pulse power machine. You get nice ground loops and things from that. I think all that can be managed, but they face a similar difficulty, and you have to show combat value and combat effectiveness. I think so far the railgun is lagging behind directed energy on doing that.
Yeah, get it demonstrated.
Red microphone.
Hi,
Tell us your name and if you're a member, and ask a question.
Locke Kuhn. I'm not a member, previous affiliate of the Cosmos Club, but I am. My question is that two or three situations. One is
Hold the microphone up to your mouth so we can hear you.
What about like a phased array radar, having phased ships, numerous 5 destroyers with the carrier, all having directing the energy against a particular incoming hypersonic, even, so that you could get enough energy on it to make a difference. Second question is that why not take the example that you set up as the killer app, which is drones, and see how they were able to penetrate into the DoD pretty quickly. There are tens of thousands of drones, as far as I know it, that are even combat drones, kamikaze drones, MQ-9s, all variety, from tens of millions of dollars down to a few thousand. So there's a recent massive development that somehow got through that maze that you were pointing at earlier. So I wonder whether directed energy can somehow do anything similar by having small lasers, really small ones that have a particular task on a Jeep, or man-carried, soldier-carried, that can begin to have an array much like the drone development had.
Let me talk to the drone, and you can.
Well, I was going to talk to the drone as well, but you go. I was going to say the drone adoption by the military did not happen quickly. It was very painful and very long.
And it is an example of what I was talking about with a focused agency. The Air Force was very resistant to having drones for surveillance. The DoD created the Defense Airborne Reconnaissance Office, Darrow in the 1980s. They put a 3-star general, General Israel, in charge of it. He got Predators in the air with sensors. He got Global Hawks into the air and built at scale in numbers into the air for use for those surveillance. It's a great example of how to overcome the resistance to a new way of doing things. But the other thing going on with drones, you're right. There are now hundreds of thousands of them all over in our military and militaries all over the world. But that is leveraged against a commercial industry. Okay, the drones as a weapon have the advantage that there's a huge commercial industry building drones for non-military applications, and the parts that they're built from are commercial parts and put together in garages and warehouses and cobbled together. The directed energy weapons as a defensive weapon to defeat them, there isn't this commercial. There isn't a commercial market that's going to buy hundreds of thousands of directed energy weapons and only a few high-end ones for the military. I agree with you. We need to start with small stuff, smaller, cheaper stuff. There are companies offering 10 kilowatt, 20 kilowatt class directed energy weapons that will fit on the back of a pickup truck. They're not going to be effective against everything, but they'll be effective against something, and they will get into the field and show the utility of these things.
Let's take a couple from the web, and then we'll go to the blue microphone, wherever that is. And then the red microphone, would you run it to somebody who has their hand up? So web first.
Okay. Dave G., not a member, but in Washington, D.C., a member of the Army, asks, most of the discussion was around hard kill. Is there another side of DEW discussion around soft kill, such as defeating comms capabilities, i.e. electronic comms defeat?
The microphones are on. You don't have to do anything with them.
So there's a boundary question here. Is that electronic warfare? And there's a whole Department of Defense thrust and effort in electronic warfare. There's certainly overlap between HPM and electronic warfare and putting more poop on target to damage communications and do that. And so most of the focus has been on dealing with the missile threat rather than jamming communications, which can be further out, and you've got over the horizon issues as well. It's a good point. It's a good question.
Certainly HPM that is effective against a front door attack on a radar would be effective in a front door attack on a comm system and could be used that way. And there is something called high power RF, electronic warfare, which is sort of trying to do that. It's not quite at the levels of volts per centimeter that the HPM people call a weapon, but people talk about how to use those things.
And then certainly people are using lasers to dazzle sensors, damage sensors, which are much easier targets than trying to blow a missile out of the air.
Yeah, the Odin system, the 8 Odins on Navy ships are specifically to dazzle, temporarily, reversibly interfere with sensors, so to make them go away, basically. Yeah, you can't say anything, I'm going to go away. If they're close enough, they may permanently, burn out some part of a camera, that's the whole mission of that system.
And this is me asking a follow-up to that, Carrie Liss, APL, a member. Is that a foot in the door for your directed energy weapons? If you have a capability with comms defeat, can you then get it actually military confidence and then exploit it and get it, boost up the power to turn it into a DW?
Well, it's interesting that comm application has the same problem that many other directed energy applications have, which is, how do I know it worked? How do I blast the guy's comm antenna, he goes silent for a minute. How do I know he just didn't shut up and he's spoofing me? And as soon as I turn off my directed energy, my microwave thing, he's back happily, chatting over his comm link. What's the damage assessment? This is part of the problem with HPM. One of the issues that's unique to it, that whether it's even worse for the so-called backdoor, where you're trying to leak energy through little cracks and holes and gaps. And okay, it gets you zap the thing and you think you had an effect. Do you really have an effect, or is he just faking it? Okay.
Thank you. The second question from the web is from Andrew Camello of Baltimore. He's not a member. He would like to know if there's any role for free electron laser directed energy weapons.
I know somebody who used to work on free electron lasers, so I'm going to hand it over to Tom.
Well, I worked on free electron lasers at Lawrence Livermore National Lab, and there was a lot of excitement of free electron lasers in the 1980s. I actually was part of a proposal proposing to build a 100 megawatt free electron laser to shoot down ballistic missiles. Okay. That never happened. That never got built. The highest power short wavelength, 1 micron-ish, propagatable through the atmosphere, free electron laser that, as far as I know, the U.S. ever did was at the Jefferson Laboratory in Virginia, and it was somewhere a little north of 10 kilowatts. And it was a hero experiment. The guy, George Neal, who was the head of that program, became a fellow of the Optical Society just for leading that experiment. The Navy was very interested in free electron lasers on ships till they took a hard look at just what it was going to take to put an electron accelerator inside of a ship and shield it, so that the sailors on the ship could survive the use of this defensive weapon. I think that free electron lasers today are great research tools for making X-rays. SLAC has an X-ray source, a free electron laser based, but as weapons, I'm not aware of anybody seriously pursuing them anymore as a directed energy, as an HEL source for a weapon.
I thought size and weight were killing them.
Yeah. The radiation tends to kill all the people around them too. So.
Okay, blue microphone, Bob, then the red microphone.
I'm Bob Hershey. I'm a member. Of the various things you mentioned, which are the furthest along in demonstrated hardware?
You were most recently in the Pentagon, so you wanted to grab this one.
Well, you've seen the Army DEM SHORAD. They're buying 4 every year. That is in fact a way around that chart. It turns out Congress allows you to buy 4 of something without going through that chart. And so the Army, you wonder why do they buy 4? Well, that's the answer.
Yeah.
And
4 per year. You can buy 4 per year without going through that chart.
They were going to buy 4 of the 300 kilowatt IFPC held trucks, except they ran out of money, and so they only bought 2. But the intent was to buy 4 again. And so they're trying to build up enough confidence to get a program of record to buy more. And so I would say the Army 50 kilowatt on a Stryker vehicle is the most mature from a total weapon system point of view. There's what they call .mil PF, which is doctrine and organization and training and maintenance and everything, including the corporal's toothbrush for the corporal who guards it. All of that folded in. How you do all that, where are you going to park it, how are you going to train your people, literally everything associated with it. The Army's done that. And most of the other systems have not come close to achieving that. And so I would say from a total weapons point of view, that's the furthest along. And then you've got the Odins. There's 11 or 10 Odins, the Dazzlers. They're on destroyers now. I won't call those are not a program of record. And it's, I think those are actually built by the Navy.
Yeah, built by Dahlgren.
But built by Dahlgren, so it's never been handed off to industry to turn into a real product. That's probably the second most mature. We have these 300 kilowatt lasers that I won't say they're laboratory because they're better than that. They're more mature. We call them transportable. And so the companies that have built them, these lasers can get moved and used for something. In fact, the first 300 kilowatt that was delivered was supposed to go into an Army truck, but there were some issues with the truck, and so there are now 2 new ones being built. The Navy is waiting on a beam director for theirs, and it's going to White Sands. And so, I won't say those are ruggedized and militarized and ready to go because they're not, but they're also not a laboratory tool either. They're in between.
So the Army's 50 kilowatt things in the Strykers are the most mature as a weapon, and in that sense, the furthest along. And we'll see how they do out in the Middle East theater.
Red microphone. Please stand up, tell us your name if you remember, and ask a question. And talk into the microphone.
I'm David Rosen. I'm a lifetime member, and I want to ask things about treaties. For these dazzling weapons, aren't there treaties against that forbid you from using a weapon that blinds you? That's number one treaty. Now you're deploying all these weapons with hydrogen fluoride.
No, those are not deployed anywhere. No hydrogen fluoride.
It's dead.
That's
Not
dead.
happening.
That's been dead for 20 years. So
Oh, okay. So
that's one of the reasons why it's dead. It's poisonous gas and explosive and so on.
I can talk about it.
Good. Okay, but again, I thought dazzling weapons were also banned.
Well,
No. There is a treaty. There's a United Nations treaty on blinding weapons, and the U.S. is a signatory to that treaty. And so the implementation
it's
of
for eyeballs. It's to blind.
is for that is the United States does not develop or deploy laser weapons designed to blind you.
A human being.
But China,
No,
other countries get to do what they want to do. I don't get to say the United States does not do that. And so you could use a laser weapon to shoot at a person as long as you don't blind them.
And
That's illegal.
And the dazzling and blinding weapons like the Odin are to blind sensors, electro-optic sensors, cameras, infrared cameras, visible cameras.
Talk into the microphone.
They can't blind someone's eye. A laser, visible laser.
It can inadvertently do that, but you're not allowed to intentionally do that. No U.S. forces is going to intentionally blind somebody. It's against the law.
There's a million things out there that can blind people, but they're not considered blinding weapons. If you stare too closely at an explosion, you could be blinded. So these weapons are not designed to blind people. They're designed to blind sensors on missiles and other projectiles.
Before any of these weapons, let me say something. There's a process called the Directed Energy Weapons Review and Approval Process, DURAP. We all have acronyms for everything. The DURAP process. And before any directed energy weapon goes into the field, goes on a ship, goes out into the Middle East or whatever, the organization that's trying to deploy this has to go through this DURAP process, which is bureaucratic, and you fill out a lot of forms, and you create the rules of engagement, and you lay down the rules when a commander can use this in the field and when he or she cannot use it, what you can shoot at, what you cannot shoot at. It's got to be acceptable to the country you're putting this in, and lots of other restrictions. Gets signed off by the chairman of the Joint Chiefs of Staff. And now, could somebody violate the rules and use it? Yeah, there's a lot of coulds, but a commander that did that, it violated the treaty and violated it, would probably be court-martialed for that. So it's not the purpose of it, and they're expressly forbidden to use it to blind human beings. Okay.
I think we'll take two more questions. So we got the blue microphone. Tim, you stand up, tell us your name and if you remember.
Thank you. My name is Tim Thomas. I'm a member of the society. I'm kind of confused here. I mean, we have a dozen or so armored vehicles destroyed every day in Ukraine by FPV drones, little tiny drones. And I was hoping that our army would have a laser defense against these things, and therefore our armored vehicles, should we engage in warfare, would not be so easily destroyed. I'm coming to the conclusion from listening to you that that's not going to happen. We're going to have to find some other way to protect our armor. That laser weapons ain't going to work.
In the very near term. Well, I can tell you what Ukraine and Russia are doing to stop drones, and that's electronic warfare.
And cope cages. They try much more primitive ways too. Shotguns,
Yep.
gloves,
The other thing we are doing
cases.
is we're buying these Coyote. What do we have?
We had a picture.
Where's the picture? Must be somewhere further out.
There it is.
Yeah, here it is. This is a tiny it's a drone killing drone.
Uh-huh.
It's a drone with a seeker, and it has enough automatic target recognition that it can, you launch it and it recognizes there's an inbound drone, an enemy drone, and it flies into it, blows up.
Okay.
And the Army is buying these. They cost, in the latest buy, they're going to cost $125,000 a piece. And they could be used to shoot down these $10,000 a piece Shahed drones that Iran is selling. So it's still not a very good cost exchange, but that's the best answer that our Army has. And our Army is buying these for our protection in places like the Middle East.
And there's no lasers associated with this.
Well, we got those 4 things on the Stryker vehicles, and they're about to go or have just been shipped out to CENTCOM in the Middle East, and we'll see how they perform. But there's only 4.
They're offensive weapons?
They're defensive. They're intended to shoot down drones, shoot down rockets, short range, unguided rockets, artilleries, mortars, soft targets like that at fairly short range. Okay, and there's only 4. And that's all we got right now.
Not that encouraging.
What is the economics of the Iron Dome system compared to that? Because they're shooting down thousands of rockets.
Each round of an Iron Dome, I've been told, is be $50,000 to $100,000 a round to shoot, and then of course you have the rest of the system. You have the launchers, you have the radars, you have the fire control, command and control, and all of that. So again, $50,000 or $100,000 per round to shoot down these Katyusha rockets that cost a couple $1,000s. It's clearly the cost exchange is not favorable. That's why the IDF is investing in the Iron Beam, which they think will have a more favorable cost exchange.
Which is
a laser beam,
100
kilowatt class laser beam. To shoot down the same kind of things.
if they got that deployed.
Next year, hopefully.
Hopefully, 2025. It's in development.
Red microphone might be our last question.
Hi, thank you so much for the talk. My name is Tej. I'm not a member. My question is regarding countermeasures. With all the countermeasures being developed right now, at what point do you think they're going to catch up with the defense capabilities, and where at some point you're going to hit some practical physical limitations, right? So what happens after that? And if I may, do you think something like a deflector shield or depth trays being in development?
Polarize the deflector shield, the Enterprise says.
I don't think we have any deflector shields coming. Every country's looking at countermeasures. Deploying them is a little more complicated. If I have several thousand cruise missiles and I want to now add an ablative coating, that's a major program and a major cost and a performance impact. And I might not want to do that.
Especially since we have only 4 laser weapons on Stryker vehicles.
Laser weapons. And I might want to change,
recoding thousands of cruise missiles.
and I can change tactics and how I use my cruise missiles. And then I can always say, instead of dwelling, for 1 or 2 seconds, do it for 3 or 4 seconds and burn through that. And so until we really start to see these things on both sides and see how it really plays out, I don't know how to answer your question about where it ends, but you can't arbitrarily put as thick of material as you want or the kind of material you want on a missile or an artillery shell and still get the performance you want and the cost you want. So like I said, there's no free lunch for everybody. It's a complicated set of trades. And again, laser weapons are not going to sweep the battlefield and be the silver bullet to solve all problems. They will be a system within a system of systems that provides value. I mean, I got asked constantly how much money we were going to save because we didn't have to buy missiles anymore if we had laser weapons. And I said, you're not going to save any money. You're going to spend more because you're going to buy the same number of missiles and maybe more missiles when we add lasers, but you'll have a lot more capability. Again, there's no free lunch.
I guess I'll ask a last question, which is the Navy has a tiered system of defense for aircraft carriers in particular, and the closest in, I think, is the phalanx system.
TWIS, yeah.
It's just basically shooting out bullets at an alarmingly fast rate.
Yep.
And hoping one of them hits.
And hopefully one of them is basically trying to put up a wall of bullets.
And they do.
And
it even works.
what about that on a scaled down version for defense, close-in defense of against drones and things like that? There's just not
So
enough range.
the military's reluctant to go that route because most of the bullets miss.
Yeah, but they're cheap.
But they then go.
They hit something
They
else.
hit something else.
Collateral damage issue.
And so it's a collateral damage issue. And if you're doing a base defense, say in Iraq, there's probably an Iraqi village downrange. You don't want to hit that.
If you're a ship at sea, the bullets just go into the water. But if you're on land, they're going to hit something on land.
Well, if you're a ship at sea, you're going to miss the missile with most of the bullets, and the ones that miss are going to go hit the ship that Tom's on.
Yeah, there's a small problem. Huh?
But you know,
There's no smart bullets in the works.
They actually are smart
Yeah,
bullets. Yeah, and if you think laser weapons are expensive, wait till you see the smart bullet.
Well, thank you guys very much for a very entertaining and interesting talk. We hope you're successful.
Thank you.
Thank you.
Before you go,
That's right.
so one more thing we want to talk about, which is we have a token of thanks, including a framed copy of the announcement of your talk signed by all the members of the General Committee. Rosette, which on its side is emblazoned with 3 stripes, symbolic of the unit of inductance, which is named for our founder, Joseph Henry, who studied inductance and helped invent the telegraph, and a copy of Volume 1 of the Philosophical Society of Washington Bulletin, which contains the president's opening speech explaining why the society is founded, what its purpose was, and has a very nice discourse on how discourse in a scientific society should take place, which I commend to everybody to read in the present environment, which doesn't seem to subscribe to that particular approach to scientific discourse. It also has summaries of some of the things that were presented at the early meetings, including a presentation on how to calculate the value of pi to 30 places. And with that, thank you guys very much.
Thank you.
You can now take your microphones to the back. No, just take them to the back. Before you go, we got a few closing announcements, mostly what the upcoming lectures are. So 2493rd lecture will be on April 5th. The speaker will be Philip DeShong, who is Emeritus Professor of Chemistry and Biochemistry at the University of Maryland. He'll be speaking about encapsulation and its application to vaccine formulation and drug delivery. If you want to know more about what's gone into developing and manufacturing the BioNTech and Moderna vaccines and many other drugs, tune into this lecture. 2494th lecture will be on April 19th. The speaker will be Richard Pyle of the Bishop Museum in Hawaii. He'll be speaking on deep ocean corals and will tell us about the innovative equipment and methods that he developed that have allowed him and others to dive to very considerable depths, way beyond the reach of your ordinary scuba diver, to study these corals and the flora and fauna that inhabit them. This particular event will be jointly, in a sense, with the Washington Academy of Sciences. So if you'd be interested to meet people from the Washington Academy, this will be a good event to come to. 2495th meeting will be on May 3rd. The speaker will be David Spergel. David is a physicist and currently is president of the Simons Foundation. He chaired the panel on unidentified aerial phenomena and likely will be speaking on that topic. 2496 will be the annual Henry Dinner and lecture and will be on May 17th. The speaker will be Brent Seals of the University of Kentucky, and he'll be speaking on recent success reading ancient scrolls from Pompeii using X-ray, computed tomography, and artificial intelligence. The work opens up a practical possibilities that hundreds of profoundly damaged scrolls found at Herculaneum eventually will be deciphered, which promises to greatly expand our access to the primary literature of Greek literature and thinking from 2,000 years ago. 2497th meeting will be on May 31st. The speaker will be Masaharu Subakura, and he will discuss health effects of the Fukushima nuclear disaster and the health effects of the efforts to deal with it at the time. We're seeking some additional financial support to bring him here from Japan, so anybody who is interested in helping us with that, please let me know. The 2498th meeting will be on June 14th, and the speaker will be former NASA Administrator Mike Griffin, who is currently co-CEO of Logic, which is spelled L-O-G-I capital Q. He recently testified for a different scale-back approach to land the U.S. on the moon, and we'll be talking about that. And the 2499th meeting, which is the last of the 20 lectures of the 2023-2024 lecture series, will be on June 29th, and the speaker will be Ben Schneiderman, and he'll be discussing about human-centered AI. Please check the website frequently for updates because things have a tendency to change despite my best efforts to keep them all the same. The site is www.pswscience.org. Let's thank all the people who worked hard to put this program together. Please return your name badges to the box at the back of the room. And with that, I'll entertain a motion to adjourn the 2492nd meeting to the social hour. Thank you, Bob. We have a second. All in favor? All opposed? The meeting is unanimously adjourned to the social hour.